There are 4 sections in the module. The first is counting, and it discusses the natural numbers, 1, 2, 3, and so on, also called the positive integers, and more generally also includes 0 and the negative integers, which is necessary because we're going to be talking about addition, multiplication and subtraction, so we need negative integers. And I should remark at this point that the sections are not of equal length by any means. So the second section on prime numbers discusses the division algorithm, which is a way of formalising division. When we divide 2 integers, we have a quotient, we have a remainder. Then we discuss prime factorisation. We show that any integer can be written as a product of primes. This is not particularly hard, but more on that matter later. And then we'll show that there are infinitely many prime numbers. Now this is not obvious, but it was first proved by the Greeks in about 300 BC in Euclid's Elements. In fact, it was probably known even before that. I never fail to, I'm always impressed with the depth of the mathematics done by the ancient Greeks. The next thing we do is the prime number theorem. We just need a little bit from that. It gives us an idea of how dense the prime numbers are, how frequent they are, and they are very frequent. The next thing we talk about is the Euclidean algorithm. This gives some important facts about the greatest common divisor of 2 integers. Finally, we show that prime factorisation is unique up to order. There are many different ways of going about factorising an integer, but we'll always end up with the same primes after we have reordered them. The third section, modular arithmetic, discusses the operations of modular, sometimes called circular, addition, multiplication, and exponentiation. And this turns out to be very important in number theory generally, and in particular in RSA cryptography. The fourth and final section is RSA public key cryptography. RSA cryptography and later developments are the basis of internet security. They're the means by which secret information is passed back and forth along the internet between individuals, banks, terrorists, and military establishments. RSA cryptography works in principle as follows. I publicly announce a method by which anybody can code up a secret message for me and then in fact publish that coded message, but only I can decode it. Everybody knows how to code the message, but nobody except me knows how to decode the message. The fact that such a method exists even is truly amazing. RSA cryptography relies fundamentally on the fact that it is almost essentially impossible to factorise large numbers. For example, numbers with 300 digits or so. So here we have two 150 digit or so prime numbers. Multiply them together and you get a 300 digit number. I publish that 300 digit number. People then can use that 300 digit number to code up their messages to me. But nobody else beside me can decode it, and that's essentially because I know the 2 factors in that 300 digit number. In principle, given enough computing power, one could factorise that 300 digit number, but it's not possible in the lifetime of the universe given existing technology. I'll also say a little about the fascinating history of RSA cryptography.